So now that we've talked about the very simple or simple-minded Java Executor interface, let's take it to the next level and look at something that goes above and beyond what's in the executor. So we're going to talk about the Executor Service. And we'll see how it provides a lot more things, and we'll see how it also depends on a lot more things in order to do its job. So quick overview here of the interface. Later we'll come and look at implementations of the interface. So what the Executor Service does is it extends Executor, and all that means is you can still call execute if you really want to, but once you start using the Executor Service, you rarely ever would want to do that because there's so many other cool things it can do. And so in addition to submitting tasks, you can also produce futures for tasks that run in the background, and then you can manage the termination of the tasks through their futures, and/or you can actually manage the worker threads that are in the pools. Cool. We'll talk about what a future is in a second. I'll show you an example. The best way to think about a future, just to get your mind in the right mode, if you ever go into a restaurant like Wendy's, where they cook your food to order, and you go up to the register and you order, a Wendy's burger or whatever they have. I'm not sure what they don't have, a Big Mac or a Whopper, but whatever the Wendy's equivalent of that stuff is. You'll order your food, and rather than waiting at the cash register for your food to be cooked to order, they will hand you back a little plastic token. It's called a table tent number. And you take the table tent number and you go off and do something, and then when your food is ready, they either bring it to you or you go pick it up. So that little plastic table tent number, that's a future. It's a promise of something that will be redeemable in the near future. Okay, so that's what the Executor Service does. As we'll see, the Executor Service relies on a bunch of other things. One of them is a future. We'll talk more about that in a second. The others are callables and runnables. Runnables get inherited from the executor interface, so we're not going to spend a whole lot of time on that other than to use it as a counterexample for the callable, which is a more interesting interface. So as you already saw before, Runnable is a one-way task that doesn't return a result, because it returns void, doesn't return anything, of course. In contrast, a callable is a two-way task that actually returns a result. And the result is of type V. So callable is a generic interface that's parameterized by the value of the type returned from call. So unlike run on a runnable, which doesn't return anything, call on a callable gives a value back. Now, we'll see later how you do something useful with this value. That takes a little bit more work. We typically use callables to run tasks asynchronously. So what does it mean to run asynchronously? It basically means that you don't block waiting for the result. What's an example of that? Well, a good example is mailing a letter, right? Let's say you want to send a letter to a friend and you're expecting a reply. I know nobody does this anymore, but 30 years ago when I was in school, we used to send letters around. And the way it works is in case you don't know, you drop the letter in a mailbox, and then you don't sit there like a hungry puppy waiting by the mailbox for the letter response to come back, right? That would be crazy. You let the post office go and deliver the mail. Your friend or whatever can write a response. They send it back to you, and then you get the letter delivered. So that's asynchronous. You don't have to sit there and wait for it. You don't block at the mailbox waiting for the response. Under the hood, this way of doing things with the Java Executor Service implements the active object pattern. So if the runnable that we talked about before was used to implement the command processor pattern, then the callable can be used to implement the active object pattern. And that basically decouples method execution, in other words, making the call, from method invocation, in other words, doing the method, such that the call and the running of the method can run in different threads, and the response can come back through some means, typically through a future, as we were just talking about. So the way this typically works is you have one thread that makes a method call. It sends a message over to another thread. That thread, when it is ready, will go ahead and run the method, and then it gets the result back to the client through some kind of future. We'll talk more about that later. So what's a future? A future is basically an object that represents the results of an asynchronous two-way task. So going back to our conversation I had with Cole a minute ago, compare and contrast Wendy's with McDonald's. Even McDonald's, by the way, is changing, but classic McDonald's would pre-cook the food. So you'd go into the McDonald's, The idea was to, give you your food as quickly as possible. They didn't really care if it was very fresh. So you had heat lamps with, Big Macs. You had heat lamps with French fries. You had a tray of pre-poured Cokes, right? Soft drinks, whatnot. And you would go in, you would say, I want a Big Mac, I want a Happy Meal or whatever. And they would say, one Happy Meal coming up. They take your money, they turn around, they grab the Big Mac, they grab the fries, they grab the drink from the cash, right? Because that's a cash. It's an L1 cash. And they would take the thing and they would hand it right back to you. That was a synchronous transaction. And the reason why you didn't have to wait very long was they had pre-cached what they had cooked. But that wasn't, good. So some people like their unhealthy fast food fresh. So Wendy's came along and said, we're going to cook everything to order for you. And so what they do, as I just mentioned a few minutes ago, is they will take your order and then rather than having you stand there waiting, synchronously blocking, waiting for the food to come, they will go off and cook your meal. And rather than have you stand in front of the cash register, which by the way would reduce transaction throughput, right? That's the whole goal, is to sell more hamburgers or more fast food. So they will cook those things asynchronously. You get a table tent number. You go off, you text your friends, you read the paper, you browse the web. Who knows what you do? You talk to your friends. And then when the food is ready, there's a couple different ways to get it to you. And one way to reclaim the future is to walk back up to the pickup window, right? And you say, hey, is there the order ready for number 12 yet? And if the answer is yes, you pick the food up. If the answer is no, you can either block at that point or go back periodically and check. So that's what's called a polling model. There's timed polling and non-timed polling or blocking polling. And then there's also the callback model, which is where they bring the food out to you when it's done. So you sit at your table, you put your table tent number there, and when you're finished, they'll bring it out. A lot of like delis do it that way, right? So you have a little stick where you put your number in there, and then they come around and give you your food. So just different ways of being able to deliver the results of asynchronous processing, right, where they're cooking food. Any questions about that? So the future is the table tent number. It's the equivalent of the table tent number represented in an object that is a way to be able to get the results of an asynchronous task. You can also do other things with futures rather than just wait for them. You can check to see if they're done by isDone. You can cancel them. You can check to see if they're canceled, and or you can get the results by blocking, or you can get the results in a timed way. So those are all the different kinds of things you can do to a future. So a future, in fact, is an object, just like other stuff. You can do things to it through its methods. And when you combine the active object pattern with the callable implementation and the executor service and so on, you can have the executor service give back a future which the client can then reclaim in some way or another. Now, it turns out that there's other variants of futures that are needed in order to be able to implement the executor service. And we're not going to talk about them in great detail right now. We'll come back and talk about them later. One of the things is something called a future task, which is basically a way to get the result back from a background thread that's doing the processing asynchronously back to the client when it needs to get the result or when the result is done. So that's one way to get it. And then there's something else called a runnable future. And this is a way to be able to execute a run method which will cause a future to complete and allow the results to be obtained. For the time being, these are implementation details, which we'll come and talk about later as we get more into the implementation of the executor service variants, cached thread pools, fixed size thread pools, and so on and so forth. There's also something else called a completableFuture, which is a variant or a subclass of future that supports so-called dependent functions and actions that trigger upon completion of things. For those of you who took the class last semester, you've got a heavy dose of completableFuture. We probably won't talk about it as much in this class, but it's quite interesting and can do a lot of cool stuff. So it's actually not part of the Java Executor framework, sadly, but you can use them together. And we'll talk more about that if we have time at the end. The executor service, this interface, is part of a whole framework of other classes. So as you can see, executor service inherits from executor, and then there's something called an abstract executor service, which is a class that is going to implement the executor service, and then it goes ahead and serves as the basis for ThreadPoolExecutor, fork join pool, and scheduled ThreadPoolExecutor. By the time we're all done, we will talk about all these things. And this is a class that factors out common code. If you're really curious, you can take a look at all the source code, which is available here at the OpenJDK website, which is pretty cool. All right, let's continue on with our discussion of Executor Service, and this will give us a chance to start talking about the key methods provided by the Executor Service. And you can see there are a whole bunch of them. So there's a lot of them. We're going to split this up into a couple of parts. The Executor Service can be used to execute individual tasks. So you can execute a runnable just by using execute. That's just the old-fashioned stuff that you get from the fact that Executor Service extends executor. That's not strictly part of the Executor Service interface, but it's implied by the fact that it extends executor. And then we have a method called submit. As we saw before, execute is a one-way task that returns void, so it has no return value, whereas submit takes a task, which is a callable, and it can be used to run two-way tasks asynchronously. So it's going to be used for two-way calls. And this is what supports what I call a synchronous future processing model. I'll explain what that means here in a second. What that means is the future that you get back from submit. You see, when you call submit, you give it a task to run, which is a two-way task, and you get back a future. And if you want to redeem the future, right, if you want to go up and get your hamburger from Wendy's, you have to go and block until the task completes successfully. At that point, you get the result back. Now, that obviously begs a bunch of questions. When should you try to block? How long should you wait? Should you put a timeout, right? It gets really complicated, and that's why Java 8 adds this really cool thing called a completableFuture to make this problem more tractable. And we'll talk about that maybe later. We'll come back and talk more about futures here in a little bit. There's also a whole pile of methods that are used to invoke collections of things. So there's something called invokeall and something called invokecany. And as the name suggests, invokeall is going to take a collection of tasks and it's going to run all of them. So it doesn't actually come back until it's finished running them all. And invokecany is going to go off and run a bunch of tasks. And whichever one finishes first, it's going to stop and return at that point. Both of these methods are a little bit squirrely in that they actually block until they're done, which is a little bit non-intuitive, because you might think that because they're returning to you a list of futures that they would not block, but oddly they block. There are ways around this, but you have to do some extra work. So the other thing to remember, in addition to the fact that these methods will block in a somewhat confusing way, don't make any changes to the collection while the processing is taking place asynchronously, because otherwise chaos and insanity will break out, because they're kind of sharing the way that Java's call by reference semantics works for objects. Things will be modified in strange and inconsistent ways if you make changes to the collections that you're passing into this. So invokeall, as I mentioned, will return a list of futures when all the tasks complete. God knows why they return a list of futures at that point. They're done, right? So that's very bizarre semantics. All the futures returned in this list are done. You just have to go through and call get on them, and they should return right away because they're done. Invokecany is used for kind of speculative computation to see which of a number of things finish first. And you can imagine some kind of algorithm that will do maybe different search routines, or it'll go search different parts of a large document to try to find the first hit. And so whenever you get the first one, all the other ones are going to be ignored, and you get the result back. The minute it finds one, it'll cancel all the ones that are still running. So that's good. It'll at least stop processing things at that point. And any other task results except for the first one that complete around the same time the first one does, in other words, have not been canceled, their results are simply ignored. Okay, so that's some of the stuff. Now we're going to talk about how to shut things down. So this, by the way, was how we create tasks and create them in a way that we can manage them by getting futures back that we could cancel, for example. Now let's talk about ways to actually control the life cycle of the Executor service itself. And there's two methods that are used for this: shutdown and shutdown now. Shutdown provides an orderly shutdown. So if you use Windows and you want to shut down your laptop, you're not really supposed to take the battery out, right? That would be called a non-graceful shutdown. That's a shutdown now. Your whole thing just evaporates. Why, by the way, would you not want to just pull the battery out of a laptop? What could be wrong with that? Yeah. Right, if there's some state you happen to have in memory that hasn't been flushed to persistent backing store, either on the hard drive or across the network or whatever, just pulling the battery out is very, very abrupt way of dealing with that, and you'll probably lose your work and it'll be uncached, which is why whenever the blue screen of death shows up, and it shows up less frequently these days than it used to, at least on Windows machines, it's usually a bad thing. You've probably lost some work. So shutdown does an orderly shutdown. It's kind of like hitting the shutdown button on your laptop, which will say, do you really want to shut down? Yes. Do you want to cancel these tasks or just let them finish? Kind of gives you some options so you can gracefully shut things down. Once you shut something down, any new tasks are ignored, right? So once shutdown is initiated, you can't have new work that comes in. Shutdown now is like pulling the battery out of your laptop, right? That is, boom, the Grim Reaper. Psh, you cut off at the knees, off of your head, doesn't stop to wait for anything. It just goes ahead and basically cancels the background threads. If there were tasks that were waiting to be run that didn't get run, however, it's not as bad as pulling out the laptop battery because everything gets killed then, but this will return back things that didn't get a chance to run yet. You can also query an executor service instance to see what state it's in. And here are some of the methods to do that. So you can say, is the executor shut down? Then the next question, is it terminated? It may be shut down, but it may not be terminated yet, so we might want to distinguish between shutting down and terminated. And the final method is await termination. You can use that after you've initiated the shutdown to wait for everything to shut down. And obviously, if you do shutdown, it may take a while longer for await termination to finish because there may still be things that are completing. Whereas if you do a shutdown now, await termination should come back pretty fast. And you can think of this as essentially a barrier synchronizer. So shutdown and await termination, or shutdown now, can be used to wait for all the threads running in the pool to exit. And you don't continue on past await termination until everything else is shut down. Okay, so that's basically the overview of part. So now that we've talked about the executor service interface in some detail, let's talk how the ThreadPoolExecutor implements the executor service. So what is the ThreadPoolExecutor? Well, ThreadPoolExecutor is an implementation of the executor service interface, and it implements this interface indirectly through something called the abstract executor service superclass. You don't necessarily have to know all the details of this unless you're really curious to see how it works under the hood. So abstract executor service extends, or rather implements, executor service, and then ThreadPoolExecutor extends the abstract executor service. So this provides a bunch of code that's factored out. The abstract executor service provides code that's factored out and shared by some other subclasses as well as ThreadPoolExecutor. We will talk about them later. Here is a portion of the ThreadPoolExecutor class. As you can see, it's pretty gigantic, lots and lots of methods, actually quite a lot more methods than you get through the executor service directly. So you can either use the ThreadPoolExecutor in its full-blown glory, or you can use it in a restricted way through the executor service. Both ways work just fine. What it does internally is it has a blocking queue that keeps track of tasks that are passed from clients to worker threads. And you can see this is going to be a worker, and so we're going to have a worker that's going to work off of stuff put in the queue in something called a work queue. And that's what's going to be used to queue up things that are tasks that come in above and beyond what's already capable of being processed given a number of threads in the pool. The queue that's used here, there's different kinds of queues, and you can dictate the characteristics of those queues through various means, either directly or by using executors factory methods. So one type of queue is called a synchronous queue, and this supports what's called a direct handoff model. So when you basically use a synchronous queue, when you start up a task, it actually doesn't queue it at all. It just basically creates a thread or finds a thread in the pool and directly hands the work to that thread. The good news with this approach is it avoids deadlock because you're not queuing anything up. The downside is you can create a lot of threads that way. And it's kind of like an all-you-can-eat buffet. You make money in an all-you-can-eat buffet as long as people don't come and eat all the food in the restaurant, right? But if you're really hungry, you could come in and have, 157 lobster tails, and then the place goes out of business, right? So that's the downside with unlimited resource access. Another type of queue you can give to a thread pool executor is called an unbounded queue. And the idea of an unbounded queue is it will help smooth out bursty requests, kind of like seasonal jobs, right? So why does Walmart hire more people over Christmas or over the holidays? It's because they know they're going to have a lot more work to do. But then once that's done, they let those people go, right? So it deals with burstiness. The downside, again, is unlimited resources. If you have an unbounded queue, then if there's lots and lots and lots of work, the queue will keep growing and growing and growing. It'll eventually consume all the memory on the machine. The third and final type of queue that you can have for a thread pool executor to queue up the work is called a bounded queue. And as the name suggests, it's just a queue that has a fixed size, like an array blocking queue. By the way, I should have said that linked blocking queue can be used for the unbounded queue implementation, so you can just have a linked list. The array bounded queue uses a fixed size array, and that, of course, will restrict the size. The good part, it limits the resource utilization. It's like following a diet, right? You have a certain number of calories you can eat, and that's it. The downside is, what should the size of the queue be? And if you pick a size that's too big, you're wasting resources. If you fix a size that's too small, you can end up with deadlock because you're trying to work on stuff and you have not enough elements to queue things up and get work done. Yes? You can dynamically set, the question was, can you dynamically set the size of a bounded queue? Yes, you can, but only when it's created. So once it's created, it's fixed. You can decide when you create it how big it is, but once it's created, it's fixed for that duration of time. It's kind of like a mortgage, right? You could have variable rates, but once you lock in, then you're stuck with that rate. Okay, so that's the end of the executor service part. Talking about thread pool executor very